So recording is on, and welcome to this practice class. I just started with the video of yesterday test that has been achieved at NASA for the core stage of the SLS launcher that should bring men to the moon, and just to see and to record the power that can be generated by rockets, and I hope that you appreciated it. I think that some of you was also yesterday to see this test that lasted, I think, about 8 minutes of a lot of propellant that was burned in these 4 thrust chambers clustered close to each other. So today we should, well, first of all, I hope that you can hear me, and because I have no news about that, and if I have no answer, I suppose that you are not hearing me, so I stop here.
Sì, professore, la sentiamo.
La sentiamo, sì.
Grazie del feedback. So we should, I consider that, okay, we have missed the class of Wednesday, but today I would like to keep our practices, and so we will go ahead with some further exercise. And unfortunately, I wasn't able to add other questions to the e-learning platform in these days. I'll hope to do it as soon as possible, hopefully during this weekend. And so today I would like to give you a first part of exercises still related to the, let's say, to the relations between different masses and the achieved propulsive delta V that we can get, and a second part related to one-dimensional flows. So as the first exercise, I would like to propose you the following. We consider a given engine and that is used with a single unit in the second stage and with 5 units in the first stage. You have seen in the video, for instance, the 4 RS-25 engines on the bottom of the SLS core. So in this case, in this exercise, we consider 5 units in the first stage and 1 unit of engine in the second stage. The one important performance parameter, I will recall that we have as important performance parameters, we have the specific impulse, but also one important parameter is the thrust-to-weight ratio. So in this case, we know that for each single engine, we have thrust-to-weight ratio beta, which will be the thrust generated by a single engine divided by the weight of this engine, which is equal to 50. You know that rockets feature high thrust-to-weight ratios. And we also know that we have an epsilon, that is the inert mass ratio of 0.11, and this is true for each stage. But if we consider the first and second stage, they have the same epsilon, which is 0.11. And both stages can also be considered to have the specific impulse equal to 4,000 meters per second. the different stages have also delta V 4,500 meters per second each. So what we want to do with this data, we would like to compute the lambda, so that means the payload mass ratio, and knowing that we have an initial acceleration, so I mean the acceleration 0.5, an initial thrust to weight ratio of 1.5. This is related to the Hoor rocket, not only the engine. So we would like to calculate this lambda and also the final acceleration of the first stage and the initial acceleration of the second stage and the final acceleration of the second stage. And we can also compare the results we obtain with those obtained without considering the engine mass. So you can think about it a few minutes so that we can better discuss together how to do this exercise.
Professore, scusi, mi sente?
Come?
Mi sente?
Sì.
Volevo chiederle, il beta, quindi è riferito al singolo motore?
Sì.
Ok, grazie.
Prego. Of course, these practice classes can also be useful to discuss possible topics that are not clear from the lectures. I would like to use these hours as much as possible to consolidate your preparation. Your knowledge and your capabilities about rocket propulsion. So what we have to do here, the first thing to keep in mind is that we have to use relations about masses, knowing what we are doing. So in this case, we have to explicitly mention the mass of the engine. And so in general, we have that the initial mass will be given by the payload, the propellant, and then the inert mass that in this case we can partition in one part, which is proportional to propellant mass. And so we call this MSP, and another part of the inert mass, which is related to the engine. And of course, our epsilon being defined in this way is something which is proportional to propellant. So we'll only use these for the MSP. You also notice that we have no single value of mass. That means that we can consider mass ratios to make our evaluations in terms of, let's say, lambda and accelerations. So it's useful to divide everything by the initial mass and look to our coefficients. Of course, considering also that this relation written here must be specialized for both stages. So we look first to the first stage. We write something like this, and we have all the information. You would exploit.
Excuse me, Professor.
Yes.
Why aren't we taking into account the mass of the engines in the epsilon term?
We are not keeping it within the epsilon because usually, yes, in principle, we can also consider epsilon including the engine mass, but this is typically done when when the engine mass is negligible with respect to other inert masses. Now we are explicitly giving the engine mass, and why it's not correct to use epsilon if the engine mass is important, because we have seen that with this relation we are considering that this inert mass is proportional to propellant mass. And of course, the engine mass is not related to propellant mass. It's related to the thrust level. And we have also talked about this when we have seen different ways of considering the effect of staging, where you have one term which is proportional to the thrust level and another term which is proportional to the propellant mass. Does it clarify?
Yes, thank you.
Well, so if we have only epsilon, it means that we are considering that everything is proportional to the propellant. If we specify the engine mass, it means that we are not considering this mass within the epsilon, which is proportional to the propellant. So this is what we are doing here. We split these two contributions to the inert mass, and we can evaluate all these terms because, of course, the propellant mass would be related to the delta V that we achieve. You recall that C, which is propellant mass over initial mass, is 1 minus E minus delta V over UEQ. And so this will give us this term. This is part of our unknown. Of course, at this moment is the relation giving us the mass of the second stage. And then we have this quantity, which will be, of course, epsilon over 1 minus epsilon MP1 over M0. This term here. This is Z1, and this is again Z1. And this Z1, of course, is obtained by replacing the value here. And finally, we have this term, which this, let's say, new term, which is related to the mass of the engine. So here we have given number of engines by the mass of the engine will be our MSE. And then we have to evaluate this MSE over M0. We can write it this way, and we can exploit our beta that relate this to thrust, relate ME to thrust. So we have NE, and ME will be F over beta G0 and we can also consider that this quantity n times by the thrust of the single engine is also F0. That is given, this F0 over GZM0 is given by our alpha. So given alpha and beta, we can obtain also this term here. So we have everything, and we calculate at this point our lambda. One minus epsilon minus alpha over beta, and the result will be 0.211. Notice that if we don't consider this mass, result would have been 0.241. So there is a significant mass of the engine. Then we move to the second stage, and we have similar. We have to proceed in a similar way, again writing this expression for the masses, and also here we'll have 1 is equal to lambda 2, and dividing by M02, right? And so we have then plus. I will have MP2 over M02, MSP2 over M02, that will be our Z2 over 1 minus epsilon. So this includes the propellant of the second stage and the inert mass of the second stage, which is proportional to propellant. And then we have now MSE over M02. So here MSE is now equal to the mass of a single engine, because you have just one. And from here I can write my ratio MSE over M02, that will be expressed in terms of, let's say, MSE over M0, M0 over M02, and the first term will be, we say that this is ME, so it means that is FE over ME beta, sorry, over G0 beta. This is MSE, which is equal to ME. Then we have to divide by M0, and then we have M0 over M02, which is 1 over lambda 1. Moreover, we can make it appear on the first term better than FE. We know that this is F0 over NE, and as a consequence we have again F0 over G0 M0, which is alpha, and so we have here NE beta lambda 1. So we have also this term. We know also how to calculate this term. Zeta, of course, will be 1 minus, is the same as zeta 1 because we have the same expression. And we can make substitutions, and we obtain that our lambda 2 is equal to 0.213. Very similar, and it would have been, as we have, except for the number of engines, stages are similar, it will be exactly the same in case of in case we neglect the engine mass. So the overall lambda will be the product lambda 1 lambda 2, and so it will be 0.045 compared to 0.058. At this point we can calculate our the acceleration given by the rocket, so without accounting for the gravity force, will be AI1, of course, is 1.5 G0, and AF will be given by the mass ratio. Of course, we have the same thrust, and so the only change will be the change of mass. That will change the acceleration, and we end with operation of the first stage with 4.62 G0. Let's look now to what happens to the second stage. The initial acceleration will be F over M02. And now our F will be the thrust given by the single engine, and it can be convenient to make appear again the initial mass, because with this we can relate the value of the engine thrust as we have done just above here. And so this will be F0 divided by N, and here I will have F0 over NE M0. And this will be again 1 over lambda 1. F0 over M0 is alpha G0. over NE lambda 1. So NE is again, of course, is 5, as we have defined at the beginning. We know the value of lambda 1, we know the value of alpha, and so it results that this will be 1.42 G0. And the final value is easily obtained by the mass ratio also here. And will be 4.37 G0. So we see that for this example, having considered 5 engines at the first stage and single engine in the second stage will allow us to have similar acceleration levels at the two stages. So this can be, it's meaningful to have different thrust level. And in particular, you also see that everything is very similar, and this is because we have that ratio 5:1 is similar to the inverse of lambda 1. And so you see that here we have this term and E lambda 1 that tell us the difference between the first and the second stage accelerations. This is I2, of course. Very good. This was the first exercise. Let me see. Yes, another interesting exercise about the thrust weight ratio. Or like now this second exercise. We would like to see what is the consequence of reaching a higher specific impulse, paying a cost in terms of engine weight. So we can imagine, for instance, we are considering, yes, we will study later the propulsion system, so I will not anticipate what I think in part you already know, but that we will go in depth later. But we can imagine that to increase the specific impulse, we have an engine, a heavier engine. So we can imagine a situation, the following situation, where we have a 2% increase of specific impulse, and that can be obtained by a 50% increase of thrust weight ratio of the engine. And so we apply this to a stage. Consider, for instance, an upper stage where we would like to realize delta V of 4 kilometers per second with epsilon 0.1 is again epsilon without the engine, and with a specific impulse, and this is the starting value or the basic value of 3.5 kilometers per second, and also this basic propulsion system has a thrust to weight ratio of 50. So given this, we like to consider the increases I mentioned before. So we would like to have, of course, the same thrust level. F is the same, and we would like to see what is better. So if it's better this engine here or the one that includes an increase of specific impulse, but also a cost in terms of the thrust to weight ratio of the engine. F is the same. So we change the specific imparts, we have the same trust, it means that we have something less in terms of mass flow rate. Let me see if you need more data. Yes, I think that we have also to provide you with information about this trust, and so we can say that we are considering an upper stage, and so we have here 0.5 M0G0. So what is better? What is the answer to the question? What is better? Or which is better?
Professore, scusi, posso fare una domanda?
Sì.
In che termini vediamo qual è il migliore? Cioè, nel senso, valutiamo payload ratio oppure...
Ecco, infatti questa era la domanda l'ultima domanda che ho fatto è: che vuol dire cosa è meglio?
Ah, ok, grazie.
Diciamo una domanda che faccio a voi, poi tra un attimo vi do la risposta, che però immagino un po' me l'ha già data anche lei. Lei cosa direbbe?
Vabbè, non l'ho fatto apposta, ma sì, cioè, dato che non abbiamo vincoli oppure altri criteri per valutare il payload ratio, direi che quello sarebbe un buon parametro, diciamo, da valutare.
Esattamente, cioè alla fine, at the end what we have, our goal is to have the maximum payload ratio. That means the minimum mass to be launched for a given payload mass, or vice versa, the maximum payload mass that we can achieve for a given initial mass. This is, let's say, for a given mission in terms of delta V, a possible improvement. So here, when I ask which is better, of course, it will be better the engine that will provide for this data the maximum payload ratio. So this is, of course, this is trust to weight. So it will be less trust to weight if we increase by 50% the weight. So is there someone who can tell me which is better? So of course, we have to use exactly the same relation as we have done in the former exercise. We have just to evaluate the differences in terms of Z, the propellant mass ratio, and of the engine weight for the two cases. So actually our value of Z will be given by it's without one, it's just a single stage here. So it's 1 minus E minus delta V over Q. And so we have these figures available, but you can compute it, and what we have is that lambda is 1 minus Z over 1 minus epsilon minus ME over M0. So we have, of course, that in the first case, ISP or UEQ is equal to 3,500 meters per second. In the second case, we have to add, let's put a prime here for the second engine, and it will be plus 2%, so the 2% will be 70 meters per second. And for the ME over M0, we can exploit again this relation here, because we have that F over ME G0 is our, let's call it again, beta. And is also equal to F over M0 G0, M0 over ME. So we are looking for this quantity, and if this is alpha equal 0.5, is the ratio F over M0 G0. So we have again that this will be ME over M0 will be alpha over beta. So in the first case, we already have our value that will be lambda equal to 0.233. In the second case, we have a different beta, and this will be W plus multiplied by 1.5. Let's cancel this. Because we have this increase of 50%, and so we have to replace the former beta by this one. So this beta prime will be beta over 1.5. So we'll have that our ME over M0 will be alpha over beta prime, and so will be alpha over beta multiplied by 1.5. Of course, we had here the mass of the engine, so it's, of course, it's easy. We just have to multiply here by 1.5. So we can see the result, and we obtain that here in the second case, the improvement of let's say the reduction of propellant mass is greater than the increment of the engine mass in these conditions, and we realize here 0.236. So it's a little improvement, but you have to consider this is still 1.3%, which is not something that we can consider negligible. So I still have another exercise, then we will just give the text, and then we'll stop. The exercise number 3 will be a case of for a reusable stage that has to provide a payload delta V of 2500 meters per second. We consider that this is a reusable stage and that we need a high delta V. We exploit only partially the aerodynamic drag, and we need a delta V of 2000 meters per second to be recovered, to land at zero velocity on the launch base. So let's say this is up and this is down. And we would like to compare the payload mass fraction that we can obtain for this delta V, considering an ASP of 3000 meters per second and an epsilon of 0.08, sorry. And we'd like to compare the payload mass fraction that we obtain with and without considering this recover. Okay, we can stop now 10 minutes, and we will resume at 1:10.
Scusi.
Prego.
Non è che potrebbe ripetere il testo gentilmente, velocemente?
Certo.
Grazie.
No, il testo è che abbiamo un veicolo riutilizzabile, uno stadio riutilizzabile che deve fornire un carico utile, scusi, non un carico utile, un delta V di 3500 metri al secondo per raggiungere, diciamo così, deve fornire questo al payload, e poi se per utilizzarlo è necessario un ulteriore delta V di 2000 metri al secondo, che è un po' inferiore perché si sfrutta, diciamo così, la resistenza aerodinamica, e vogliamo confrontare il rapporto di carico utile che si ottiene con un razzo con le stesse caratteristiche, che è in grado di fornire, diciamo che fornisca solo i 3500 metri al secondo necessari al payload, oppure con un razzo riutilizzabile che deve appunto aggiungere anche la fase di rientro di 2000 metri al secondo.
Va bene, grazie.
Prego.
Professore,
Sì?
Sì, volevo fare una domanda sull'esercizio precedente, diciamo sulla parte finale.
Sì.
Sì, volevo chiedere, c'è un motivo per il quale i valori di accelerazione sono molto vicini, specialmente quelli finali?
Sta dicendo su quale esercizio? Dove non l'abbiamo calcolato l'accelerazione, giusto?
Sì, abbiamo calcolato, erano pari a 4,62 G0.
Ok, quello precedente, sì. Allora lì il fatto che siano simili è quello, diciamo, l'avevo commentato alla fine dicendo che è legato proprio al fatto che noi abbiamo regolato la spinta passando da 5 propulsori a 1.
Ok,
E questo numero 5 è un numero abbastanza magico, tra virgolette, per il caso specifico perché è praticamente pari all'inverso di lambda. Abbiamo che lambda è 0,2, grosso modo, del primo stadio, e il numero di propulsori è 5. Quindi quando andiamo a vedere quella relazione, vediamo che c'è esattamente alfa diviso numero di propulsori per lambda 1 che viene più o meno alfa, e quindi sostanzialmente siamo allo stesso livello di spinta. Questo perché abbiamo ridotto sostanzialmente il livello della spinta della stessa quantità di quanto si è ridotta la massa tra il primo e il secondo stadio.
ok, perfetto, grazie.
Prego. Not give you the solution now. So in this case, I will not give you the solution now. I leave it to you for. I will give you the solution on the website. So I leave it to you. You have just to consider that at the end of let's say of the lifting operation, there will be a release of the payload, so that we have to consider in the descent that we have is like in case of staging, we have removed part of the mass because we have delivered it towards, let's say, the continue the second part that would be, for instance, another stage or something like this. So we have to be careful about that. But I'd like to leave it to you so that you will try. In this second part, I would like, as I mentioned at the beginning, I would like to make now some exercise related to our one-dimensional flow analysis. And we have a first exercise concerning the area change. And we consider a flow in a channel with a circular cross section. We know the inlet conditions is P1, 100 bar, T1 is 3000 Kelvin, and M, the molar mass, is 12 kilogram per kilomole. Gamma is 1.2. Mass flow rate is 200 kilogram per second. And cross-sectional diameter is 0.4 meters. These are the inlet conditions. We would like to evaluate now what is this is D1. What will be D2? The diameter of the exit section where we have that Mach number is equal to 0.7. I would like then to discuss what happens if we assume that D2 is equal to 0.2 meters. So of course, this is the case of isentropic flow. We have only area change, so we have that Sm and Se are equal to 0. The only driver is the area change. And as you know, for this case, we can exploit the isentropic relations, and we know that total temperature, total pressure will be constant. And you also know that we have a relation between the ratio of area to critical area and the Mach number. So for this reason, the first thing to do is to obtain the inlet Mach number. Anybody is able to calculate this inlet Mach number?
Come ρ A forse, dalla portata in massa, ricaviamo la velocità, abbiamo la temperatura, quindi la velocità del suono e possiamo ricavare il Mach.
Sì, ovviamente la ρ bisogna calcolarla. So of course velocity is hidden in the mass flow rate, and the area is of course given through the diameter, and we have two state variables, so we have all state variables. So we know the speed of sound, we know the density, we know everything we need. So of course you need to recall that R is point something. We can see 0.4, and this is Joule, not kilogram, is kilomole Kelvin. And so we know this M, and this R is 692.9. We know R, we know gamma, we know T, so that A is equal to 1579.3 meters per second, and where we need U, so dot M is rho UA, A is pi d squared 4. And this is 0.12566 square meter. Rho is P over RT. So it's 4.81 kilogram per cubic meter. And finally, we can obtain that U1 is equal to dot M over rho 1 E1 will be 330.8 meters per second, resulting as M1 0.209. So the first step is completed. We have computed our inlet Mach number, and now what was the goal was to compute the diameter, or let's say the area. So we should evaluate the area in the second position where the Mach number is equal to 0.7. We note that we have both conditions are in the subsonic regime, so this can be obtained through a single angle, let's say, of the single sign of the variation of the area, because so we are both values are subsonic. Actually, we have an increase of Mach number, so it means that we have a converging channel, and we can evaluate this ratio A2 over A1 through the area law. So we have A2 over A1 is M1 over M2, 1 plus gamma minus 1 half M2 squared, 1 plus gamma minus half M1 squared, gamma plus 1, twice gamma minus 1. And we use this with our gamma, which is 1.2, and we use our two values of Mach number. And with this relation, we realize sorry, I have written the inverse. Let me just wait a minute. 2.63 is 0.38. The results of this operation. That means, of course, that there will be a ratio d2 over d1, which will be 0.616. So 617. Of course, d2 over d1 will be the square root of a2 over a1. So this allows us to calculate the value of d2, which will be 0.246 meters. We can move to the second question. What happens with d2 0.2 meters? So you can recognize that it's something less than this d2, so it's further diameter reduction, and so we have to be careful because it could be something, let's say, smaller than allowed with that inlet Mach number, because we may have chugging. So we can, first of all, we should check if this is allowable or not, and we can compare our diameter, which is now 0.2 meters, with the critical one. The critical one, which is obtained, of course, as D1 over the square root of A1 over A star. And this term, which is under square root, will be given as 1 over m, 1 plus gamma 1/2 m squared, gamma plus 1/2, and which is the same, of course, written for m2 equal to 1. And this ratio is 2.895. As a consequence, we have that our D star will be 0.235 meters, telling that our given diameter is not allowed with that inlet Mach number. And it means that if we consider this diameter, the mass flow rate must be necessarily reduced, and we can also evaluate this reduction so we have that the new mass flow rate, let's say B over the mass flow rate A can be expressed as, let's say, also the ratio of, we have the same total conditions. So at Mach equal to 1, we will have the same condition as a trot. So the mass flow rate will be only related to trot area. So we have here this trot area, let's say that we have calculated here with this diameter, is our trot area A. And we have that here, this will be, of course, the two trot area that we are considering, the one of A, which is the one corresponding to 0.235 meters, and the one corresponding to the required diameter, which is 0.2 meters. And this has to be, of course, is area ratio, so must be squared. And this tells us that the mass flow rate will be, like, make this operation 0.235 is 0.724. So we have considered 70%, 72% of the initial mass flow rate. And this will be, if I calculation are correct, yes, it's 38% less, and it will be this quantity rather than the given 200 kilogram per second. So if we reduce this diameter, we start from a 2.46 diameter where we had Mach number 0.7 at the exit and the corresponding mass flow rate that we knew. Now we squeeze, let's say, the trot. If we reduce diameter, we realize choking conditions, and because of these choking conditions, only this 72% of the initial mass flow rate can flow through our converging channel. The second exercise, now I would like to consider something related to friction. So we consider the second case of those that we have analyzed, the one where the driving potential is now only friction. So we have no contribution of mass addition, heat addition, and area change. So we like to consider a cooling channel where it's flowing gaseous methane, and we know that the hydraulic diameter and the length. So we are cooling, our cooling gas is methane with molar mass of 16 kilogram per kilomole, and we know that we have hydraulic diameter of 2 millimeters and the length of 1 meter. So consider that this can be something reasonable for practical applications. And we consider that what is, let's say a little bit farther from the application, because we consider constant gamma ideal gas for the methane, we assume here gamma 1.3, and conditions such that methane has a density of 80 kilogram per cubic meter and a pressure of 100 bar. So we know that the inlet velocity is 50 meters per second and the friction coefficient is 0.05. And we would like to see, to evaluate the resulting pressure losses. As done before, our universal gas constant is 8,314.4 joule kilomole Kelvin. Just to think a minute about that. We will proceed similarly to what we have done to the exercise before, except that we are changing now the driving potential. So of course, the first thing to do is again to evaluate the inlet Mach number and then to exploit the, let's say, the critical relation that we have in flow with friction. This was the relation. And so we can now we should think how to exploit this relation for our purpose. So here the D is the hydraulic diameter. We have seen this, we have commented shortly when we introduced this the momentum equation and the friction factor. And yes, this is the critical length. So it's the length where the flow will choke for a given inlet Mach number. So this is something that we can evaluate from this relation. Of course, we can express everything in terms of this FL over D, which can be convenient. For instance, in this case, we can, well, once you obtain your Mach number, and we can proceed as done before, we can calculate, we have P1, we have rho 1, so we can calculate also T through the R and M, so that T1 is 240.56 Kelvin, and we have that A1 square root gamma RT1 403.11, and so as we know the velocity here, we have that M1 is 0.124. As a consequence, we have our FL1 star over D, which is 59.36. So we know that we would like to see here in this drawing where is our outlet condition, and hopefully it will not shock from this Mach number 0.1, will not have shocking in 1 meter. If this is the case, it means that we have a position here corresponding to, if this is L1 star, we will have also L2 star, sorry, not this one, but this one. This will be for a point 2, when we have M2 here, we'll have still a length to be considered to reach our 1 unit Mach number. So what is this distance? This distance is, of course, the length of the channel, so it's our L, and we see that L must be equal to L1 star minus L2 star. So we can multiply by F and divide by D. So we have F L over D will be F L1 star over D minus F L2 star over D. The first term, we have data available, so FL over D is equal to something. Of course, is 0.05. 1 over diameter is 2 millimeter. And so this is 1,500, and so it's 25. Very good. So we know these two quantities. It follows this one. That will be F L2 star over D will be equal, must be equal to 34.36. Now from this we can try to use this relation and get from it the Mach number. Of course, it cannot be directly inverted, so we have to consider a couple of tentative values. For instance, we can try with M2. What do you expect here? Something more, of course, of M1. So we try with 0.2 to see if it's already enough, or we need more. We have a higher acceleration, and we check that with 0.2 we would have for our length 20. So it must be more. To get more for this length, it means that you have a lower Mach number. You should move in this direction. So we have to reduce Mach number to consider that here we need to stay at 34 rather than at 20. So I try with point. We can interpolate and consider here this. Try to linearize it some way and say that this is, let's say, 34 is 14 over the difference which was with L1 it should be over 39, 14 over 39, and the 14 over 39 should be the difference, should be normalized with respect to the difference 0.2, 0.124. So in this case, if you do so, you obtain this is 0.165 more or less, and it results that it would be 31.74 our FL2 star over T. So we are closer, but we have still to reduce the Mach number because we have to increase the distance with respect to the choking position, and we can make further attempts up to reach the final value, which is M2.1593. That yield our 34.357, which is the correct one. So at this point, once we have obtained our exit Mach number, we can calculate the pressure ratio, total pressure ratio, that I recall has the same expression as the areas, the ratio of areas for the isentropic case. And with these two Mach numbers, we obtain that this ratio is 0.783. That means that our delta P over P, of course this is 1, would be 0.2167. And this is our loss, 21.6 bar, because 100 bar. So our delta P0 is what we had to compute, is 21.67 bar. You can also get you consider this is a case where T01 is equal to 0.2 because it's an adiabatic case, so it's easy to evaluate T2 over T1 will be 1 plus delta M1 squared, 1 plus delta M2 squared, and you get your temperature T2 will be slightly less than the initial one because of the acceleration, and so we can also calculate the speed of sound and exit velocity, which has been increased to 64.15 meters per second. And you can compare this result with the one that is obtained without considering compressibility effects, so consider constant speed, and you can obtain that instead of having this result here, you would obtain, let's say, at constant speed, .25 bar. This is the result of this expression that is valid for liquids or for compressible flows, so for gases, if you consider constant velocity, because this is also can be expressed also as delta P0 over 0 of 1/2 gamma m squared FL over D. And if you go back to the theory, you know that this P0 over P0 is minus 1/2 gamma m squared F over D dx. So if this is constant, you obtain this relation, and if you replace m squared with u squared, v squared, velocity is u or v, sorry, u squared over a squared, which is gamma p over rho, you have the same relation. So these become identical. So what happens in case of gases is that to have constant speed, it means that you need to do something that compensates the increase of the Mach number. So this can be, for instance, a change of diameter, of cross-section diameter, that makes our channel diverging. So you have that here, we have a constant cross-section channel, you give some divergence that would slow down the flow, and that compensate, let's say, the thickening of the boundary layer that actually occurs in the real case, and that would increase the velocity, as we have seen here by this expression. So we still have a little time for, let's see, another exercise. I would like to consider now mass addition, or better, let's consider this case. Oh, this is simple. We have three positions that you would like to consider, and here I marked with these lines the existence of a solid propellant. So we'll have from 1 to 2, we'll have mass addition, and from 2 to 3, we have a converging nozzle that would be isentropic. So we'd like to compute for given mass flow rate, gamma, gas constant, throat area. We'd like to calculate the pressure, total pressure here in 2 and in 1, and also the different dimension that we have to consider. So let's say the area A2 and throat diameter D2, and so on. Of course, D1 is equal to D2. So what we assume, the data are that M3, this is choked nozzle, so we have M3 equal to 1. We consider gamma 1.2. R is 320 kilogram Kelvin. Dot M is 1.5 kilogram per second. M2 is 0.4, and M1 we consider 0. So we have a wall here. This is propellant, and this is wall. So we have injection here, and the exhaust of the gas here in 3. Further data, RT0, 2000 Kelvin, and AT, so this is known. It's not, yes, it's not an unknown, and is 0.0003 square meters. So with this information, we should evaluate our DT, D2, and A2, P02, and P01. So we can exploit the different relations. In particular, we will consider the case of mass addition with y equal to 0, because we assume that we have a flow in the normal direction here, and also we assume that T0i is equal to T0. with this assumption, we can exploit the relation A2 over A3, of the area for getting A2 over A3. This will be a function of M2, M3 gamma. And we can exploit also the relation of mass flow rate. That would be rho UA, of course. And this will be useful because we have so we have this, but we need this to evaluate, let's say, our second state variable, because we know ratios, but we have here just this temperature. So we know temperature, we know Mach number somewhere, or let's say everywhere. And so we need something that allows us to evaluate our static pressure or density. And this will be obtained starting from here. And then you can apply the relations that we have seen for the mass addition. In particular, you can go back and see that with M1 equal to 0, we have P02 over P01 is equal to 1 plus delta M2 squared to gamma over gamma minus 1 over 1 plus gamma M2 squared. So this, you can go back to the relations we have got in class and see that this relation is can be applied to in this way for the present test case. At the end, the most interesting result will be the total pressure, and we see that we have isentropic flow here between 2 and 3, so that P02 is equal to P03 will be equal to 75 bar, and whereas we have P01 that will be equal to 81.9 bar. And so also here you can work in it and get this check with this result. So this ends this practice class, and we will see next Monday.